Hello everyone, welcome to the presentation today. In this talk, I will present our work, SpecTaint, Speculative Taint Analysis for Discovering Spectre Gadget. My name is Zhen Xiaoqi and I'm from UC Riverside. Since 2018, the emergence of Spectre attack has drawn a lot of attention. This type of attacks exploit an optimization feature of modern processors, which is known as speculative execution. And this feature is deployed by most modern processors. Therefore, Spectre potentially affects a wide range of chips made by Intel, AMD, and ARM. This is a very typical example of a Spectre bound check bypass gadget, also known as Spectre BCB. In this example, if IDX is greater than array len, and the processor mispredict the branch outcome to be taken, then the following instructions will be executed in speculation. Therefore, the first array access will load an out-of-bound value from memory. Then the loaded value is used as the index to access another array. This will result in cache line changes for the data array, and the cache line index is related to the loaded value E. Therefore, an attacker can infer the out-of-bound value through cache side channels. Many chip vendors have provided mitigation strategies for Spectre attacks. For instance, Intel shows that Spectre BCB gadget can be mitigated at software level, including but not limited to process isolation, branch masking, and offense insertion. The offense instruction can effectively stop speculative execution after a branch. Here in this example, if we add an offense instruction after the branch, it stops the speculative execution, thereby preventing potential memory leakage. However, the challenge is where to insert the offense instruction. Patching all branches in a program is infeasible because it might introduce large runtime overhead. To ensure the security of the software without thwarting the efficiency, the goal is to find the minimal set of Spectre gadgets in the program and only patch those gadgets. There are some existing techniques for Spectre BCB gadget detection. Some of them use static analysis. For instance, RH-Scanner is a tool developed by Red Hat community. It searches for Spectre instruction patterns in the assembly code. And 007 was published in TSE 19. It extracts the control flow graph from the target program and meanwhile performs static taint analysis for gadget detection. Some works use dynamic analysis. For instance, Spectator from SP20. It performs symbolic execution on both targets of a branch. One is normal execution path, and the other one is speculative path. Then it compares the memory access pattern in these two execution mode. SpecFuzz is another work from Usenix 20. It exposes speculation to fuzzing. More specifically, it performs compiler instrumentation to force the execution of untaken branches. Meanwhile, it detects memory violation as a sign of speculative leakage. However, there are some fundamental limitations about these techniques. First, for static approaches, they failed to exploit the execution passes statically due to indirect jumps, function returns in the program. Therefore, it introduced false negatives. Moreover, 007 suffers from the overtainting issue due to its conservative alias analysis and non-analyzable function calls, which introduce false positives. SpecFuzz is limited by its simplistic simulation and detection strategy because it needs to guarantee the fuzzing throughput, which, according to our evaluation, introduces both false positives and negatives. For Spectator, which uses symbolic execution, it is by nature not scalable and it requires manual configurations when analyzing large programs. To solve those limitations, we propose our approach, SpecTaint. SpecTaint is also a dynamic approach. It relies on external fathers to generate sys input and runs the target program inside a system emulator. To simulate speculative execution, it performs dynamic binary instrumentation to redirect control flows. Along simulated speculative passes, it performs dynamic taint tracking to detect potential Spectre gadget. Let's use the same gadget as an example. For a conditional branch, it first replaces the PC with the untaken branch in the emulator. Then it executes the untaken branch. Before that, execution states, such as registers, are saved. Then it enters the simulated speculative execution. During this phase, it conducts dynamic taint analysis to track the data dependency between instructions. In this example, we mark user input as taint source, and we identify that IDX is tainted, which means it can be controlled by user input. Here, it captures a gadget that first loads a secret from an input controllable location, then leaks the secret through cache side channels. In other words, there are data dependencies between those instructions, and therefore those instructions can form a Spectre gadget. When terminating conditions are met, such as reaching the speculative execution window, it restores the execution state to the previously saved state, and also restore any memory modification happened during speculative execution. Then it can continue the normal execution of the program. While this example illustrates a simple case of detecting the gadget, there are more technical challenges that we need to take care of. For instance, multiple misprediction could happen in speculation, so we need to handle nested speculative execution and path explosion. We also need to carefully handle exceptions that happen during speculative execution. Moreover, we need to formally define the pattern of Spectre gadgets based on taint traces. Due to the time limit, I will not go into details about this, and all the details can be found in our paper. Here are some evaluation results. We have 3 datasets. First, we collected 15 Spectre samples. These are simple code snippets like the example I presented earlier. The second dataset contains 6 real-world programs, which is the same dataset used by SpecFuzz. Since there's no ground truth in real-world programs, we created a synthetic dataset by instrumenting 15 samples into 6 real-world programs. And we have a total of 52 gadgets in 6 programs. More details about how this dataset is constructed can be found in our paper. Then we compare SpecTaint with 3 baseline techniques on these 3 datasets. First is the synthetic dataset. In this experiment, only inserted gadgets are considered true positives. For tools that utilize taint analysis, such as 007 and SpecTaint, we first only taint the input bytes that control inserted gadgets. In this setting, we can see that 007 still produce many false positives and negatives, while SpecTaint can achieve a 100% precision. For dynamic analysis approaches such as SpecFuzz and SpecTaint, we first run HomeFuzz for 10 hours to collect seed input. Then we run these tools with the same seed. For SpecTaint, we mark all input bytes as taint source. As presented in this table, overall, SpecTaint has higher precision and recall than other baseline tools. Then we compare with SpecFuzz on 6 real-world programs without any inserted gadget. We first run SpecFuzz for 10 hours to reproduce the results reported in their paper. Then we use the same seed inputs to run SpecTaint. As can be seen in this table, SpecTaint reported less number of gadgets. To further understand the results, we manually inspect the gadgets reported by SpecFuzz and SpecTaint and verify the exploitability of those gadgets. As shown in this table, SpecFuzz produced many gadgets that are not exploitable, which are considered false positives, and SpecTaint has much higher precision rate. This table shows the runtime performance of SpecTaint. SpecTaint extends the system emulator, which by nature inherits its overhead. In theory, SpecTaint should pay more overhead for analysis. As can be seen from this table, the analysis time ranged from around half an hour to 17 hours, and it depends on the program size and number of seeds input. For SpecFuzz, its analysis engine is closely coupled with fuzzing. Therefore, it's hard to compare the analysis time with SpecFuzz. And in the evaluation, we run SpecFuzz for 10 hours and collect the results. Then we send reported gadgets to an automatic patching tool provided by SpecFuzz, and we compare the runtime after patching. Here, full hardening means patching all conditional branches in the program. On average, the overhead after patching reduced 55% compared with SpecFuzz patching, and 73% compared with full hardening. This result shows that SpecTaint can ensure the security of the program without introducing large overhead. In this figure, we show an example of a Spectre BCB gadget that is uniquely detected by SpecTaint. This gadget is found in Brotli, a compressing and decompressing program. We mark user inputs as temp source, and here we detect that the variable transform in IDX is tainted, and the bound check is performed in this line. Then in this function, transform IDX is used as an index to perform an array access as defined by this macro. Here, it first uses transform IDX to access the transforms array. Then the loaded value is used as an index to access another array. Therefore, attacker can infer the value in transform IDX through cached side channels. This gadget is detected by SpecTaint. It demonstrates that SpecTaint has a precise gadget pattern. And when given the same seeds input, SpecTaint can achieve a higher speculative path coverage. In summary, we proposed a dynamic Spectre gadget detection approach. Our approach enables dynamic taint analysis on speculative passes, and it can achieve higher precision and recall than existing approaches with reasonable efficiency. Moreover, it disclosed new Spectre gadgets from real-world programs. Our project will be open-sourced. The benchmark and code can be found in this link. Thank you for your time. If you have any questions, please let me know.